Good. So thank you so much for joining once again. Today we want to tackle something new, something different, and we want to consider sampling distributions. Um, One way or the other, all of us have been involved in one form of sampling, or yeah, or the other. We've done a lot of things in our daily activities that have involved sampling. Okay, it's not different. Just that we are going to apply mathematics to other things that we've been doing in our normal lives. Okay, so sampling distributions, just a simple and then a fun way of understanding sampling. So this session takes an introductory view into the theory of sampling. Okay, and sampling is used in place of complete enumeration and or yeah, where sometimes we need to learn about the larger population, and we do this in reducing cost and saving time and all of that. So this session will go through, as I said in the beginning, the mathematics of sampling, and we provide ways to make inferences using the sample data. So these are my session objectives. You should learn how to, you should be able to understand the importance of sampling, sampling distribution, sampling error, we do some mathematics using sampling distribution for normal populations, central limit theorem, and also we calculate probabilities using the sampling distribution. Some of these stuff we are well aware of, so you will see how we can go through. So proportions, probabilities, sample proportions, population proportions, all of those things we would take note of them. Okay, who else cannot hear me? I think I am loud and clear. Can you all hear me? Before we start. Okay, so we continue with what we were saying. These are the session goals, and these are the things that we want to do as far as this course is concerned. And you're reading list chapter 7 of the recommended tests, either Grosvenor or Anderson and Srini. You should find a lot of information concerning sampling over there. Okay, so all of us know about populations and samples, right? If we were in class, I would have covered this and I would have asked you questions about that. But a population is basically the set of all individuals of interest, right? I think when we were doing hypergeometric distribution, we mentioned certain things about population and then also about sample. And we also know that a sample is a subset of the population. So, for instance, if you take 1,000 voters selected at random for an interview, it is selected from a population of all likely voters, right? Students of Eugene is a population. All students of Eugene is a population of the school. But if I pick, let's say, 500 students for something, maybe a work or a study, then I've selected a sample of the students. So basically, those are the things that we are looking out for. So we would take notes and then yeah, look at it once again. Then we have a sample. Yeah. So we have, let's say, a population that is full of A to Z, right? The population of alphabets. Then we pick a certain sample. We pick a sample of alphabets for whatever we intend to do, right? So basically, population is the entire membership in the group, and the sample just represents a representation of the population, a part of the population that you are going to use to make conclusions. Now, I think we should ask something questions. Okay, so why do you think sampling is important in the things that we want to do? Why is sampling important? Can someone help us? As usual, please raise your hand and then I can see you and call you. Why is sampling important? All right. Thanks, Eugenia. Okay, Eugenia, since you can hear me, you can answer me now. Why is okay, Grace? Why is sampling important? Hold on. Grace, yeah, why is sampling important?
So I think sampling is important because just in case the experiment you want to carry out is destructive, you wouldn't have to destroy all the things you have. If you sample it out, at least you get to destroy just a few. So
Yeah.
it won't be destructive to everything.
Yeah, that's a very good example. Reason. Can you give us an example of some of these destructive stuff that we are talking about? Yeah.
Okay. So let's say you have a collection of maybe gadgets,
Hmm.
and then you want to find out which ones are faulty. Let's say you
Yeah.
have 100 of them. I want to find out the percentage of or the probability of maybe some of it being faulty or something. If you take all the 100 gadgets and then you decide to test it on all the 100, by the time you're done, you'd have spot all your 100 gadgets.
Yeah.
And if you
Yeah.
take a few out, even if it is destructive, it's just a few that will get spots in the end.
Exactly. Exactly. That is very. That's a good example. Thank you. All right, Maureen.
Okay.
Oh, okay, Maureen. Let me hear from you, Maureen. Yeah.
Hello.
Yeah.
Yeah. So sometimes the population is also so large that if we don't sample it out, it will take a lot of time to do the research. It will be
Yeah.
very expensive as well, and
Yeah.
there will be so many errors because you get bored. Now you are doing the research on so many people or so many things that
Wow.
you are.
So you've talked about time. You've talked about cost, and then you've talked about accuracy. In the sense, and someone will argue with you with the accuracy bit, but I think you can explain your point out. Okay. Let me hear you. Yes, Okay, I think Enoch is out. So basically, what that you guys have said is true, and I like some of the illustrations that has been given, and I think we should even be done with the class because everybody understand. Yeah, so to avoid time wasting, and as you said, to save time, you save resources, and then you save cost. And with this destructive nature, I think that she really explained it. Assuming I want to, um, I go to the hospital and I'm undergoing a test. What do? They take a sample of your blood. They don't need all the 14 liters of blood that is within you to make draw whatever conclusions that they want to draw concerning your health, right? So if they draw all the 14 liters of blood that is within you, you will die, isn't it? So because of the destructive nature, assuming a car manufacturing company is trying to test the crash, um, how do I say how the cars can withstand crash. So they subject the cars to certain levels of impact. If I do a fleet of 1,000 cars, I won't subject all the fleets to a crash test, right? I'll just take a sample and subject it to them because if you end up subjecting all of them to a crash test, you end up destroying all the fleet of cars that you manufactured, right? So these are certain things. And then Maureen talked about the time saving and then the cost saving. So yeah, less time consuming than a census, less costly to administer, and then the destructive nature of the cost, and to minimize errors from boredom, as Maureen said. And it's possible to obtain statistical results from a sufficiently high precision and all that. Now, if sampling is so advantageous, do you think there are possible disadvantages in conducting a sample? Possible dangers, possible disadvantages, and all that. Since Eugenia is back, maybe Eugenia can help us answer this. Yeah.
So, yeah, I think there are possible disadvantages. Yeah, but I think sometimes the sample we might take might not be accurate. So
Right.
maybe, yeah,
Yeah. Continue.
yeah,
Continue. Continue. I
so
like I like
maybe,
where you're going. So
yeah, so maybe if you are finding the probability, you have a lot of balls in a box, and you are finding the probability that maybe um three are soft, or like all of them are, just say three are soft, you might choose maybe all three and will be soft, but maybe the whole box is not full of soft balls, but because you sampled out soft balls, your probability like look like all like you get it.
All right. Thank
Yeah.
you. Yeah. Any other disadvantage? Enoch. Okay, Enoch, you're back. Enoch. Enoch. Okay. I don't know why Enoch is off. Okay, let's continue. Yes. Any other disadvantage of sampling or danger of sampling? I think what Eugenia was trying to say also was the fact that much as sampling help us to minimize error, if you do a complete enumeration well, you get an accurate overview, right? But sometimes if you don't sample well also, you're really going to get erroneous figures and you're going to make erroneous inferences. And we will see, we will give you certain examples to see why such is the case. So sampling is important, but make sure you sample well, right? The sampling that you are choosing, the sample that you are choosing, make sure it is representative of the population. For instance, if I am doing a research on the effectiveness of this government, okay, and I choose only, say, I sample out only MPP sympathizers, what do you think would be the response of this work that I'm doing, this research that I consider? Can anybody help us? Yeah, Eugenia.
So please, I didn't get a question. Is it like you are trying to see the effectiveness of this government, like the
Yeah,
NPP
yeah.
government right
And then
now?
the
So
people
you
I
sample NPP.
supporters, yeah, or enthusiasts, or
Then they think that the government is doing well and that there's nothing going wrong.
yeah, yeah, yeah.
Yeah, so they'll
That
give
is,
an inaccurate
yeah.
decision choice.
What if I sample only, let's say, NDC or majority of the NDC people?
So then NPP government has done. They would
Yeah,
really scrutinize the government.
very much, right? So you
Yes,
see that
please.
in all of these ways of sampling, I might have sampled a lot of people, I might have sampled so much, but then the responses will be biased because they have their own biases towards how the government is performing and all. And even if I sample, let's say, perhaps people from the south only, or people only from the north, the responses may still be biased, right? And I may not get the actual import of what I want to do because the sample is not representative enough. So when we are talking about a representative sample, we are talking about a kind of sample that reflects the characteristics of the population. Okay, in a sense that whatever property of that is present in the population, we should at least see some of most of these properties within the sample, if not all. Okay, so that the sample can be representative enough to make very accurate inferences. Okay, so there are various forms of sampling techniques that we can use, and we have very two broad techniques: probability sampling technique and then non-probability sampling technique. And for probability sampling techniques, they are done in such a way that each person within the population or each unit within the population have the same chances of being selected, right? But in non-probability samples, that's not what happens. People do not have equal probability of being selected. So sampling techniques like simple random sampling, systematic sampling, stratified cluster sampling are all forms of probability sampling techniques. If we had the time, we could have gone through each of these. And then we also have non-probability sampling techniques such as judgmental sampling, where somebody chooses the sample based on its own biases or its own judgments. And then convenience sampling, mostly that's what we do. We do convenience sampling, or do we think we are doing simple random sampling? But they just pick the people because perhaps they were close to them, they were easy to access and all that. If I'm doing a study of students' behavior, because perhaps I'm close to level 300 students, I would want to select them up for my sample. It's a very convenient sample I'm choosing to do that way. So there are various forms of, and then we even have haphazard sampling. Yes, you come like those kind of things. It doesn't really follow any sampling probabilistic or proper sampling approach, but just being taking the samples just like somehow would say just like that, right? So basically that is what we have, and that is what we intend to do as far as this is concerned. So some key definitions. The first one is concerning what a population is. So a population is the entire collection of the units or the thing under consideration. And a descriptive measure that is computed from a population data is what we will call a parameter. Okay, so a parameter could be, assuming that I'm computing the mean from the population, then the population mean will be an example of a parameter. Okay, now a sample is a portion of the population that is being used or selected for the analysis, and any descriptive measure that is computed from the sample data is what we will term as the sample statistic. So we have a population parameter and then a sample statistic. So a sample statistic could be the sample mean or the sample proportion or the sample standard deviation, the sample correlation coefficient, and then the population parameter could be the population mean, the population proportion, the population standard deviation, the population correlation coefficient, and so on and so forth. Okay, so when it comes to statistics, there are very two broad branches that we normally deal with. The first is what we term as descriptive statistics, where in this form of descriptive statistics, we are just describing the things we see using the graphs, the charts, the summary measures like the means, the standard deviations, and all that. We are just describing the phenomenon, describing the data. But there is another one that we term as inferential statistics. And in inferential statistics, we are making statements about the population, okay, by examining the results of the sample, okay, um, by doing what we call an inferential statistics. We look at the sample and then you make conclusions based on the population. Now, a lot of you guys do inferential statistics in the kitchen, right? What kind of inferential statistics do you normally do in the kitchen? Can someone help us? A very practical example about that. Um, Somebody is called Ekaabano. Please, I've been asking you to put in your real names. So please do change some of these names. Okay. All right. So yes, can anybody help us? Okay. So when you get to places like this, someone is preparing food, and the person wants to, as it were, um, test the salt content of the food. What do? They pick a spoonful of the soup or the stew, and then they taste. Right now, based on what you witnessed, how well the thing tasted, whether it was good or not, you make conclusions out of it, right? So out of it, you say that, okay, it's too salty, so let me do something about it, or it is not, there's not much salt, so let me add more salt to it. So you made a conclusion by from just examining a spoonful of soup, and you use that to make a conclusion of an entire pot of soup. You didn't have to drink the entire pot of soup before you could make this, you could come to this conclusion. So in other sense, you are making an inference, okay, of the population based on your sample. And in the Bible, Paul really does this very well. I mean, Paul would just say that, he lists a lot of things, he talks and talks and talks, and then he comes back to say, okay, what shall we say then? Right? So in a sense that he intends to make conclusion as to all that he has stated, all that he has said, based on the analysis that he has made. So inferential statistics allows us to make deductions, allows us to make conclusions and statements about the population by examining the results of the sample. So yes, by definition, you draw sample conclusions and make decisions about the population based on the sample results. Okay. All right. So these are some of the sampling statistics that we saw. I think I explained the differences between a population parameter and also a sample statistic. And mostly sample statistics are used to estimate the population parameters. Most of the time, the population parameters are unknown because of the difficulty to carry out a complete enumeration. We mostly use the sample statistic to estimate the value of the true and mostly unknown population parameter. All right, so the sample mean X bar will be an estimate of the population mean mu. Okay, so from here you need to be able to understand what these notations are. Sample mean represented as X bar, population mean represented as mu. And the catch is this: different samples will provide different estimates of different of the population parameter, right? And they have potential variability, and also there are possible sampling error that would come. Now, because we are not using an entire enumeration, we are not using the entire population data, there is always a chance that the sample statistic that you have calculated will not be the exact value as the population parameter. And there's also the chance that anytime you select a different sample, we are going to get a different estimate, right? The difference between the population parameter and the sample statistic is what we term as the sampling error. Okay, the sampling error. So when we talk about sampling error, it is the difference between the population parameter and the corresponding sample statistic. So mostly it is what S bar minus mu. Whether mu minus S bar minus mu is not really much of our focus, but the focus largely is the value, the magnitude of this error. If it is too wide, it means that your sample error is quite huge, whether it is positive or it's negative, right? So most of the time you do things or you select samples that minimizes in such a way that your sampling error would be minimized. Okay, so in the previous example, we have this a population of 12 projects, and then their size, and the average size has been calculated to be 158,971. That becomes our population parameter. Now, based on this, we select a sample of 5 projects, and we select out of randomly, we selected a sample of 5, and we calculate the error. And the error was termed as the difference between the sample statistic and then also the population proportion. That gives us an error of 6,912. 88. So here we can conclude that the sample exceeds the population by about 6,988 square feet, right? So these are some of the ways that you can help to conclude compute the sample error, and also to make very good inferences with regards to that. So another example, if the population mean is 99.5 degrees, and then a sample of n equals to 5 yield a mean of 99.2, then what's the sample error? The sample error is just minus 0.3 degrees. Very simple basic calculations that will not require a lot of tears. Another example is here. I think you can solve this, and then you move on. Please make sure you try your hands on some of these questions. Okay, let's get into more interesting stuff. So if you remember what I said early on, I mentioned that different samples will give you different values for the statistics. For instance, we are going to have different, if for every different sample that I choose within the population, there's a high chance that I'm going to obtain a different sample statistic. Okay, so assuming we have a class attendance of say 103 people, if I take that to be my population and I'm interested in maybe your ages, and I want to find the average age based on a sample, and I select a sample of 10, and I compute the average age, and I select another sample of 10, I compute the average age, I select another sample of 10, I select more and more samples of 10. Each of the average ages in the sample of 10 that I'll compute, I'll end up selecting. For each run of the selection, I'll get a different average age, right? If I put all of these means together and examine its distribution, then we term that as a sampling distribution. And you repeat after me, sampling distribution. Okay, so the expected, the sampling distribution comes as a result of the different, the distribution of the different sample values, sample statistics that you select from the population. And this is an example that we have. So for the first sample, we have the mean. For the second sample, we have a mean. For the third sample, we have a mean. For the fourth sample, we have a mean also. So a sampling distribution is a distribution of the possible values of a statistic for a given sample selected from a population. So since every sample has a mean and standard deviation, a distribution can be constructed for all the means from the possible samples that could be taken from the population. So we can always construct a distribution. It comes back to us to learn about population and probability distributions, isn't it? That is how interesting and fun math is. They are always interlinked in one way or the other. Well, it's debatable. Okay. Now, there was an important question that I think we missed in the determination of sampling error, right? One of the things is that the sampling error will always reduce, or they reduce as the sample size increases. Why do you think this is the case? Can anybody help us? Why do you think the sampling error would decrease as the sample size increases? Okay, Maureen.
I think that it means that the representation is increasing, so the biases will reduce, which means you are capturing a larger population, percentage of the population. So you have, a good representation of the entire population.
Okay, so the sample gets closer and closer to the population, right? So it begins to assume more properties of the population. So it begins to have a more accurate information. And that's why most of the time when you are conducting a research or whatsoever, which you will be doing in your project work, and next semester you'll be tackling more of research methods, you understand why there's a need for you to have a very a sample that is good enough to meet the objectives of the work that you are doing. Okay. Yeah, school is interesting. It's fun. Okay, so we were touching on sampling distribution, and I think we should continue with that. Okay, so it brings us back to a very important theorem that if you have a population that is normally distributed, and once again, if you've never paid attention, please do pay attention for this one. Okay, if you have a population that is normally distributed that has a mean of mu, okay, and a standard deviation of sigma, then the sampling distribution of x bar, we are not talking about x. We are talking about the sampling distribution of the sample means. Remember that we have selected various samples from a population, and each time we select a sample, they give us a mean, right? So the sampling distribution of those means that we have collected is also normally distributed, okay? And it is normally distributed with a mean mu that represents the population mean, and then the standard deviation, which we can also term as the standard error. But the standard deviation is calculated as sigma divided by the square root of n. Okay, so in other words, the sampling distribution of the means coming from a population which is normally distributed is also normally distributed, and it has a mean of mu, which corresponds to the population mean, and the standard deviation of sigma divided by the square root of n. And these theorems have been proven rigorously. Okay, and we can prove some of these. But and so if we want to standardize and help us to compute probabilities and other stuff, it means that you see the usual thing we used to do when we were standardizing. If you remember, when we were standardizing for yesterday's class for a normally distributed value, and you were checking whether the probability of a value lying within a sample, we said z is equal to what, x minus, okay, so this is what we said, right, this is what we said that z is equal to um, yeah, we said that z is equal to x minus mu over 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 sigma, right, over sigma. Let me see the standard deviation. This is no. So we said x minus the mean divided by the standard deviation, right? That this is what we were doing, right? But now, what we are saying is that we are looking out for the sampling distribution of the sample mean. So in place of x, we have what, x bar, okay? And in place of sigma, we now have sigma divided by the square root of n. So we are interested, when you are trying to find the sampling distribution of the means or of the sample means, it's no longer x minus mu over sigma, because you're not dealing with the points, but it's now x bar, which is the sample mean, minus the mu, which is the population mean, divided by sigma divided by the square root of n. Okay. Now, what if the population is not a normal population? Remember that the theorem said that if a population is normal, okay, what if the population is not a normally distributed population? Then you can apply what we call a central limit theorem. And this central limit theorem is one of the, arguably, one of the breakthroughs in statistics and then in sampling theory. Sampling distribution, just hold on. So as I was saying, the central limit theorem is a very important theorem that has originated in statistics and in sampling theorem. And what it means is that we are saying that if the population is not normal, okay, then the sample means from the population will be approximately normal, as long as the sample size is what is large enough. Okay, if the population is not normal, here we talked of that if the population is normal. So if the population is normal and it's irrespective of the size of the sample, right? Then we have this and the sampling distribution of the means also normal. Okay, but here if the population is not normal, then sample means from the population will be approximately normal as long as the size is large enough. Now the question we would ask ourselves is how large is large? How large is the samples or should the sample size be? Is there a number to it? Is there a certain value to it? But before we answer that, I think there's an illustration. And of course, if someone can help me answer that, you can put on your hand and then you'd help me answer. Okay, so we want to ask the question of how large is large. First of all, as we said, I'm coming back to this illustration. So you see that this blue curve here, okay, is a distribution, but it's a skewed distribution. Okay. Now, this blue curve becomes approximately normal, or the sampling distributions from this population becomes approximately normal when the sample sizes increase. Okay. So irrespective of what the shape of the population is or what the distribution of the population is, sample values from that distribution becomes approximately normal. Okay. And this happens when the sample sizes are large, becomes larger and larger. And the question that I'm asking is how large is large? Now, how large depends largely on the distribution of the population, right? Some of them, if it is fairly normal, if just a small amount would suffice, but others would also require a larger sample, right? So that is why, okay, yeah, others will require a larger sample. So but then we have come up with certain numbers that help us or serve as a guide. So for most distributions, a sample size of more than 30 would suffice, would give you a distribution that is fairly normal. Other books also talk about 25, others also talk about 30. So, I mean, we are going to use either of these numbers in what we do. But I think 30 is what has been in use for the most part. For very fairly symmetric distributions, as I mentioned, that generally depends on the shape of the distribution. Even a sample size of more than 15 would do, right? So this is the situation we find ourselves, and this is what we will be looking at. So let's take for example, we have a population that has a mean of 8, right, and a standard deviation of 3, and then a random sample of size 36 is selected. What's the probability that the sample mean is between 7.8 and then 8.2? Okay, now we didn't mention that the population has a normal distribution or not, right? But then we've seen that the sample size is large enough. So what it means is that we can approximate using the central limit theorem. And from the central limit theorem, you realize that we can approximate it. The mean will still be mu, and then the standard deviation will still be sigma divided by the square root of n. So given that, we say that since n is 30, the sampling distribution is approximately normal with a mean of mu x, and then the standard deviation is the standard error, or the standard deviation is standard deviation divided by the square root of n. That gives us 3 divided by the square root of 36. That gives us, I think, 0.5. Yeah, yeah. Okay, so the same ways we were doing we're using to calculate probabilities using the normal distribution is the same approach that we would be employing in this situation. Remember that we are finding the probability that the sample mean is between 7.8 and then 8.2. Okay, we want to find the probability that sample mean is between 7.8 and 8.2, which is the same as the probability that Of course, if your X bar is the sample mean, right? Is the sample mean, then I'm looking for the probability that X bar, which is the sample mean, is okay, 7.8 lies between X bar, which also lies between 8.2. This is what we are looking at for basically. Okay, so that is what we'll be doing. So you still have to go through those process of standardization. X bar minus mu divided by the standard error, right? So we have 3 over root 36 given as the standard error for one part. You get the z value here. Then you get the z value also for the other part. So eventually, this is the probability that we are going to determine. At this stage, you guys will be, let's say, experts at reading from normal distribution tables. Yeah, but generally, this is what we have, and we can easily infer these values from the normal distribution table. If you refer to our previous lecture and the previous video, you will see how the normal distributions and the probabilities were calculated from the normal distribution tables. Okay, let's take more questions, and I think that would bring us home. All right, so suppose that the population is known to be normally distributed. Okay, so for this one, I would want a volunteer to help me with this question. Someone to help or guide all of us through the solution. Just raise your hand and then I'll call you. Okay, Maureen.
Please, I have a question first
Oh,
about the size. How large is large enough? I saw somewhere that it's greater than or equal to 30. I wanted to know if 30 can be part of the sample size.
yeah. Mostly if it's 30 or above, we consider that. That's why I was even saying that some books even use samples as large as 25, and it's okay. So that is fine. How large is large really depends on the distribution, the distribution of the population. But generally, a sample of size 30 or more is considered as large enough. Okay, so Lawrence and Maureen will take us through the questions. So I'll let Maureen start, and then Lawrence, you continue. Okay. All right. So Maureen, let's start. You can read the question and then we move on. So don't turn off your mics. Let's just keep it on. Okay, Maureen.
Suppose that a population is known to be normally distributed with mu of 2000 and standard deviation of 230. If a random sample of size n is equal to 8 is selected, calculate the probability that the sample mean will exceed 2100.
Okay, so let's get the data and the information that we need. What's the population size? Okay, we don't even need the population size. What's the mean? What's the population mean?
2000.
2000. What's the population standard deviation?
230.
230, right? What's the sample size? Let's call it n. Sample size is what? 8, right? And then what's the required probability? What are you looking for?
Calculate the probability that the sample mean will exceed 2100.
The sample mean exceeds, right, 2100. So basically you're looking for the probability that mathematically, how do you express this? Lawrence, how do you express this mathematically?
So P of X is greater than 2100.
Is it just P of X because you're looking at the sample mean? The sample mean.
Oh, sorry, P of X bar.
P of X bar, right? P of X bar is what?
Is greater than 2100.
Is greater than, exceeds, so it's greater than 2100. So this is what we are looking for, right? So since this is what we are looking for, we know that, of course, X bar is the sample mean, right? So I think that should have even be let X bar be the sample mean, right? Because of the difficulty with typing the X bar, that's why I'm doing this the sample means drawn from the population. Okay, so how do we, the next step is for us to standardize, right?
Yes, please.
Yeah, so how do you standardize? Yes, Lawrence.
So Z is equal to the
That is X bar minus minus mu, right?
all standard deviation.
All over standard deviation. Okay.
So,
Standard deviation. Is it just the standard deviation?
Over root of n.
Standard deviation divided by the square root of n, right?
Yes, please.
Something like this, right?
Yes. So it will be 2,100.
Okay, so you have 2,100
minus 2,000.
minus 2,000. Okay.
Or 230.
30 divided by the square root of
230.
8. 230. Okay.
Yeah.
230.
Yes, please.
Divided by
yes, or square root of
8.
Square root of. Yeah.
Square root of 8.
So,
okay. So just put everything together. The numerator is 900, right?
yes.
And the denominator is what? You can just evaluate it and then you tell us.
Where's my calculator?
Okay, Maureen, if you have the value, you can just tell us. Okay.
Okay.
I think I have it. It's 81.31, right? 81.3172. So what is 900 divided by that? Okay, so 900 divided by that.
No, it's 100, not 900. It's
100.
2,000.
Oh, okay,
Yeah.
it's 100.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
Yeah. Thank you.
I had 0.1537.
I think you should check it again.
So I think 1.23.
Yeah.
Let me check it again.
1.23. Yeah, that's correct. It's 1.229 and some coins, but that's really it. So when you are so this is what we have. I think it's 1.23. Okay, so I think we are still not done yet, right?
Yes.
We have to continue by evaluating. So what does it mean? It means that the probability that X bar is greater than 2,000 is the same as what? The probability that Z, right? Z is greater than what? 1.23, isn't it?
Yes.
Okay. Now, I think that Maureen, you should help us draw the standard normal distribution curve. Yes, Lawrence.
Please, why not is equal to 1 minus probability that Z is less than 1.
I think we'll get there. But first of all, we want to draw the normal distribution curve and see how these ones look like. I understand what you're saying because eventually that's what we are going to do, isn't it?
Yeah.
Yeah.
Yes, please.
Yeah, but for the sake of the class, we should just go a bit of a step-by-step nature. Okay, so this is where the 0 is, right? For a normal. And then where would the 1.23 be? Somewhere here. 1.23, somewhere here. Okay, so are we going to the left of Z or to the right of Z?
So to the right.
To the right. So this is the area of interest, right? So we need to find the Z table that corresponds to this, right?
Yes.
I don't know whether I still have my standard normal tables. Let's see. Okay. So please check your standard normal tables, distribution tables, and then give me the value. I think you should have those things present. So okay, so let's see. I can get a copy here. Normal tables. Very good. So I have my copy here. Good. So you're looking for 1.23, right? So where do we get it? Yeah. Yeah.
1.2.
So you have the 1.2 here, right? And then the 0.032 is also here. So where do they intersect?
0.89065.
Very good. So basically what it means is that, and as Lawrence was saying, this based on the shape, this is the same as 1 minus the probability that z is less than or equal to 1.23, isn't it? Right. So from the tables, so which is the same as 1 minus what we have. All the value 0.89065, right? 0.65. So when we subtract from 1, what do you get? 0.1.
0.10935.
Okay, I mean you can approximate this and becomes about 1.0.11, isn't it? So basically that is the probability that we are looking for. Okay, yeah, very good. I think Eunice, Eugenia, Ernest, thanks so much for following. I think your comments are the same as we saw. Okay, so that is good. At least it shows that you are also paying attention. Okay, so Grace, do you have a question or a contribution? Let's hear from you. Yeah, yeah.
Okay, so I thought that if the random or the sample size is greater than 30 or 15, that's when you use the random distribution.
Okay, what we are doing, okay, let's go back to the theorem. Okay, let me just finish with this question and then I will explain what is happening here for you to see. Okay, so sorry about that. So what we are looking out for here is basically simple. When you are done, I mean, this is the probability that you are getting, right? 0.1093. Okay. So Grace, what we've been talking about is that we want to be able to find the probability that the sample mean lies within a certain value. Okay. We are now looking at the distribution of the sample. Okay. And in looking at the distribution of the sample, we mentioned that if you have the sample being selected from a normal population that has a mean and then a standard deviation, then the distribution of that sample is also normally distributed. Okay, so if that is the case, then when you are trying to find the probability that the sample mean will be a certain figure or lie within a certain interval, you are going to treat it like the way you would if you were doing a normal distribution. Okay, you just do x bar minus mu. Just that this time it's not x minus mu, but it's what the x bar minus mu divided by the standard error. And this time it's not the usual sigma that you are using, but the standard error is now sigma divided by the square root of n. Okay. But if you are trying to look at a population, the sampling distribution of a certain population, which is not normally distributed, okay, then first of all, you have to, before you can approximate it to a normal distribution, that population has to be large enough. Okay, and
Yeah.
how large is a sample of size we use mostly 30 or above. You understand? So if you look at this, the first question we solved, they didn't say anything about the distribution of the population. Okay, but we could approximate it to a normal distribution because the sample size was large. You catch? Right. But for this other question that we just solved, okay, we know that the population is what's normally
Normally
distributed. So although the sample size was small, we could still approximate it using the normal distribution to calculate the probabilities. I hope that is
So
okay.
it's because of that way there that the population was normally distributed.
It's very key for you. And then if it's not there, you will still see a sample size that is larger enough. If all of these are not there, if the population is not normal and the sample is not large enough, it will be difficult to use the normal distribution to approximate it and then calculate the probabilities out of it. That means that they reflect other distributions. It could be binomial or Poisson or any other distribution that they will be dealing with. But as far as the normal distribution is concerned, this is how things should be done.
All right, thank you.
Okay, you're welcome. Okay, Eugenia. Yeah. Yes.
So please question.
Yes.
Yeah. So please assume this question was not normally distributed and they still gave us a sample of 8. Do we have to choose different samples to do it?
Not necessarily. If it is an exam and the sample size is small and then the population is not normally distributed, it tells you we cannot necessarily approximate using the central limit theorem because it wouldn't apply. So you may have to look at what distribution the population is. Is it binomial? Is it Poisson? That warrants a different solution approach. Okay. But for the purpose of this course and all of that things, we are dealing with how you apply the central limit theorem and also how you get to know that the population is fairly normally distributed. So we are working within the confines of the theorem, okay, in order to see what is going on. So that is basically what we are doing. Okay. All right. But if it's a real research that you are doing and you want to really approximate using the central limit theorem, then you would have to ensure that your sample is large enough so that such an approximation can be done. Evelyn, yes.
Sir, please, I want to see the solution again.
Okay.
The one we solved, not this one, the other one.
This one.
Yeah. Please let it go down small. I want to.
Are we wrong?
No, I want to be sure of the answers. I was lost. That's why I wanted.
Oh, okay. Okay. Are you okay now?
Thank you, sir.
All right. All right. Let's move on.
Yeah, I'm okay.
Yeah. Let's move on. Okay. So basically, that is what we have. So there are more examples that we can do, right? But I think we should. You can go and then try your hands on that, and then you guys will be fine. Okay. So that, and you know that there's another example here. Maybe we could try this. Okay, where is the lady who just answered the last question? Grace. No, that was Evelyn. Evelyn, can you help us go through this question so that you don't get confused?
Sir, I'm trying to understand. So
don't worry. So use this question to understand. Please read. Let's go.
Helping.
Sorry.
Manager of United States. Hello.
Yeah, I can hear you.
Hello.
Okay.
Hello.
Okay, Evelyn, your network is a bit bad, so I'll pardon you for now. But
Hello.
Can someone help us? Evelyn's network is not so good. Can someone volunteer for us? Okay, so Janet and Esther, yeah, the two of you can help us. So Jane and then
Okay.
Esther, yeah. All right, Jane, you can read for us.
Okay, thank you. The branch manager for United Savings and Loan in Seaside, Virginia, has worked with her employees in an effort to reduce the waiting time for customers at the bank. Recently, she and the team concluded that average waiting time is now down to 3.5 minutes, with a standard deviation equal to 1 minute. However, before making a statement at the managers' meeting, this branch manager wanted to double check that the process was working as thought. To make this check, she randomly sampled 25 customers and recorded the time they had to wait. She discovered that mean wait time for this sample of customers was 4.2 minutes. Based on the team's claims about waiting time, what is the probability that a sample mean for N is 25 people would be as large or larger than 4.2 minutes? What should the manager conclude based on these data?
Okay, so we have a long winding story and statements. What do you understand about this before we even move on? What are they trying to do? So the branch manager for United Savings has worked with employees in order to reduce the waiting time. So reduction of waiting time. Recently, they concluded that waiting time is now down to what, 3.5, and a standard deviation of what, 1. But before making that statement, they want to double check that the process is working as thought, right? To make this check, she randomly sampled 25 customers and recorded the time they had to wait. Then they discovered that the average waiting time is 4 minutes. I think one of you is getting a phone call. It will give us some feedback. So, all right. So she discovered that the mean wait time out of this sample was 4.2 minutes. Based on the team's claims about waiting time, what is the probability that a sample of N equals 25 will be as large or larger than 4.2 minutes? So you're making a claim that your mean average waiting time is 3.5 minutes, right? And now you pick a sample and now the sample is telling you the mean waiting time is 4.2 minutes. Maybe it was just something error or something, but we have to test this. And we want to find the probability that for a sample of 25 people, the sample mean would be large or larger than 4.2 minutes. And of course, what will be the implications of this? So let's move on. Is it Jane or Esther? Yeah. Oh, Esther, I asked you to talk, right? Okay, so Esther,
Yes, please.
let's start. What do we do?
We have to bring out all the, so we look for
The
the
parameters,
mean.
right?
Yes,
Yeah.
please.
So of course, first we talk about what should be the mean. S bar is the mean, isn't it?
Yes, please.
The mean waiting time, right?
Yes,
Mean
please.
mean waiting time for sample, right? Okay.
Yes, please.
Now what's the population mean?
3.5 minutes.
3.5 minutes. So we have that. We have 3.5 minutes. And then the standard deviation of what? 1.0.
1
Right.
minute.
Right. What does the sample mean?
4.2.
It's 4.2. And then the sample size is what?
25.
5. Okay. So you have all of that available here. So what's the probability we are looking for? What's the required probability?
Please, can we go back to the question? I think I
Okay,
missed
okay,
it.
all right. So the required probability is what?
That the sample mean would be as large or larger than. Oh, okay. So whether X bar is greater than or equal to
Yeah, yeah,
4.2.
yeah. So by you for now, let's write it in words, right? Probability that
Yes, please.
sample mean is what is as large or larger
Or larger than
than
4.
4.2, isn't it?
Yes, please.
That would mean that we have mathematically probably that S bar is what greater or equal to what 4.2, isn't it?
Yes, please.
Okay, now let's standardize. So how do you calculate for a Z? I don't need to write all these again. So let me just copy and paste. So Z is this, right? So how do we put in the values? So let's help me compute the Z.
So 4.2 minus 1 point, sorry,
The
yes,
population mean.
1.0.
The population mean. The sample population is not 1.0.
Oh, 3.5, sorry.
3.5. Okay. Then divided by the standard deviation is what 1, right?
1.0
And then the sample size
over
is what?
square root of 25.
Square root of 25 is 5. So let me just do that, isn't it? Okay.
Yes, please.
What do we get? What do we get?
Please hold on.
Okay. Junior says is 0.14, right? Okay. So that is good. So it means that it's good. All of you guys are following. That's great. So it means that this is actually the same as probability that Z is less than or equal to 1.4, isn't it? Oh, it's 0.14, right?
Yes, please.
0.14. Okay, so let's go back to the normal distribution and then see how we sketch this, right? So this is our normal distribution. Of course, this is where we have the 0, right? Yeah, I think Jane went offline, so if I can bring her back. Okay, so where's the 1.4? Sorry, it's 0.14, right? 0.14. Okay, Jane, are you here?
Yes, please.
Okay, so we are looking for the probability that Z is greater or equal to 0.14. Where should be the shaded portion?
Z is greater than or equal to 0.14. I think at the right side of 0.14.
This side, right? Okay,
Yes,
so as Lawrence mentioned, is the same as this portion here is the same as 1 minus the probability, right, that Z is less or sorry, Z is less or equal to 0.14, right? And
sir, please, will it be Z
Please,
is
will we
less than
add
or
the
no,
equal
no, no, no,
to?
there's no equal to. Yeah, thanks.
Yeah.
All right, all right, thanks. So from the statistical table, what do you have? What do you have? I think you can easily read, right? So 0.1 is here.
0.55567.
Very good, very good. So it's actually 1 minus 0.55567. And what do you get as the final answer? Yeah. Someone said the Z is 3.5. No, okay. No, that's so the 0.14 is correct, isn't it?
No.
I actually got 3.5, but because the person said 0.14,
Oh,
I
so
want
it's not
to.
0.14. Hey, Junior.
Yeah.
So it's what? It's 3.5.
3.5.
Yes, that's what I got.
Hey, Junior. Please, so this one is going to YouTube. Okay. All right. So but they will understand. Very good. So what do you get? So that means that this is 3.5, right? This also 3.5, right? 3.5 is huge. Let's see if we even have it. Yeah, so 3.5. What's the probability from here? 3.50, right? 0. What?
99977.
Okay, so that is 1 minus 0.99977. What do you get?
0.00023.
2, 3. Okay. So this is not 0.14, please. This is 3.5, right? This is 3.5. So let's take note of that. Okay. So thank you so much for helping us. So that is basically what we have. And mute. Oh, Esther, your hand is up before we continue. Yes. Or is it the old hand, right? I think so. Yeah. Okay, Maureen, you have a question.
Yes, please. So from the question, they first sample 25 customers and they had the 4.2 minutes.
Yeah.
So is the question asking if we'll get more than 4.2 if we sample another 25?
No, what they're saying is that okay, that a sample of 25, what the probability that it should be as large, the mean will be larger than 4.2 minutes for a certain sample of 25 that we will pick, or for every sample of 25 that we will pick. What's the probability that the sample mean will be larger than 4.2 minutes? That is what we are asking. Okay. So the question is actually based on the sample of 25 people. Yes, Eben.
Sir, please, can you go back to the solution?
Okay.
Yeah. And yeah, can you go to again? Because I didn't understand up to the part where we got the 3.5.
Oh, it's just based on this formula that we use, based on the relation between z and then x bar, and it's following from all the stuff that we've done from the top. So when we get a 3.5, it's actually 4.2 minus 3.5. 4.2 is the x bar, 3.5 is the mean, divided by the standard deviation over 1 over the square root of the sample size. That gave us the 3.5. Then we plug in the 3.5 into the standard normal table to get the probability. So it's nothing new. It's nothing new. Once you go through the calculations, it will be okay for you. All right. Eunice, you're welcome, Eben. Eunice.
Yeah, sir.
Yep.
Sir, please, can you hear me?
I can hear you.
Yeah. All right. So please, the question didn't state explicitly that it's normally distributed.
Yeah, but the sample size was large enough.
25.
The sample was large enough for us to use.
But so you said it's 30 and above.
I mentioned that some texts also use 25. It's large enough for us to consider using a normal distribution. So that is fine. Okay.
So 25. Okay,
I don't want you guys to be fixated on like it is this or that, but it depends. Some talk about 25 or more, others talk about 30 or more. And these numbers are quite large enough for us to use.
But please, can it be lesser than, okay, can it be 15 or more?
15, no. 15, no, unless the distribution, the parent distribution was fairly symmetric, then 15 would suffice. But 15 is, for general purposes, 15 is quite small. 25, fine, but 15 is small. Okay, last question, Eugenia.
Thank you.
So because my question is quite related to Eunice's own.
Okay,
yeah,
so.
But I wanted to ask, like, in a question like this, how would you know if it's not normally distributed? You just say it is, or you have to
Yeah,
provide
it will be stated. Most of the time it's stated. Yeah. Because you can't tell. All right. Okay, so I think you're still behind time. Let's move on. Good. So you see that the probability that the mean would exceed 4.2 is almost is zero. It's like 0.000 something. It's almost negligible. What does it mean? Hey, where are the ladies who are helping me? Who are they? Okay, Eben, since your hand is up, you are not going to ask a question. You're going to answer my question.
So it was an old hand.
Yeah, but so you keep it on. What should the manager conclude based on the data? We found that the probability that the time would exceed 4.2 is actually negligible, like 0.00023. What should be the manager's conclusion?
Okay, wait. Can you re-ask the question? Like what you just said before this?
I said you realize that the probability that the sample mean will go beyond 4.2 is very low, 0.00023.
Okay.
What should the manager conclude based on this data?
The manager should conclude that the waiting time is actually because it's too small. What the manager got was too small. It won't really affect the table, the what the employee said, the 4.2 minutes. So she should take it as 25 people do take 4.2 or larger.
Okay, I can see you are really trying. Yeah, but all right, Eugenia, yes.
So please, I want to try.
Okay, yeah.
Yeah. I think the manager should conclude that the mean waiting time would not be greater than 4.2 minutes.
Yeah. The chances that it will be 4.2 minutes or more is very, very low. It's very, very low. Yeah. So there can be, as we said, there can be some credibility in her claim, right? Because that 4.2 that she obtained could just be as a result of a sampling error that she did. Perhaps if she picks another sample, the mean waiting time would really come down, because the chances of she getting 4.2 is low. Okay, so in business math, in quantitative methods, because we are business people, we are not just interested in the final answer. See, that's the beauty about it. We are also interested in your ability to interpret the figures. Okay, so let's take note of that. So let's do something new. We just have some few minutes more and then we close. Population proportion. So just as sample mean measures a summary measure of population values, we also have what we call the sample proportion, which would also measure the population proportion. Okay, so basically it's almost the same thing we've been doing, just that this time you're no longer dealing with means, but you're dealing with proportions, another parameter. So the population parameter is actually the population proportion, and then the sample statistic is actually the sample proportion. And the sample proportion is mostly given as the number of successes or the number of people with the required attribute that you are looking for over the sample size. You know, people keep on making statements that unemployment rate, let's say 20% or so. Mostly, instead of using means, we use proportions to make our claims, to make our statements, and to create certain emphasis that we want to create, right? So how do we look at the sampling distribution of a sample proportion? Okay. Now, we can approximate that by looking at this. The sample proportion can be approximated into a normal distribution, okay? If the sample size multiplied by the probability of success, or the proportion itself, is greater than or equal to 5. Once again, if the sample size multiplied by the proportion is greater than or equal to 5, or if n times 1 minus p is less than or equal to 5. And this can be approximately normal with a mean of p and then a standard deviation of P times 1 minus P divided by N. Please, let's take note. The population proportion is P and the sample proportion is P bar. Okay, population proportion is P, sample proportion is P bar. So in some of your books, the population proportion, they use pi to represent it, pi. Like the one we have in math, circle, yeah. And then the sample proportion, they use the P to represent it. So don't get them mixed up. All right. So in order to standardize, it's basically P bar minus P, sample proportion minus the population proportion, divided by P into 1 minus P over the square root of N. So the same approach that we used. So if the true proportion of voters who support a certain proposition A is 0.4, so you have the population proportion, right? What is the probability that a sample of size 200 yields a sample proportion between 0.4 and then 0.45? So basically, you are looking out for the probability that the sample proportion will lie between 0.4 and then 0.45. You have a sample size of 200 and then the true proportion is 0.4. So we standardize, right? Now we first check that NP is actually greater than or equal to 5. So we can use normality to solve this problem. So basically what we have is, first they calculated the sample, this part, the denominator, so that life can be easier, right? So the denominator gives us 0.3464. That is P 1 minus P divided by the square root of divided by N, all being operated under the square root sign. The same approach of standardization, then we can read from the normal distribution table, and it works like the same thing for us. So we can find the probability that the data lies between 0.4 and 0.45, and that gives us this amount, and then we can find the respective probabilities. There are other questions that you can try. I want you to take your time and go through these questions, and if there's any problem, you can send me an email and then we can work it out. I think this will be a very good place to end. I wish you all the best. All right. Any questions?